Welcome to the optical communication course. Today we will learn that extrinsic absorption. Now we have seen that intrinsic absorption earlier. In the intrinsic absorptions, we say that absorption is due to the pure silica glass. Okay, that is about the absorption due to the pure silica glass, and because of their basic metallic structure and that basic metallic structure, that loss will occur at a near infrared region. So that is we say it is about the intrinsic absorption. Now in the case of extrinsic absorption, in the what happened because in intrinsic absorption that is about a that source is about nothing but when we design any particular glass, in that case there may be some impurities to be added. Okay, while making the glass, that impurity is to be added. Okay, that impurities in the particular glass at the time of manufacturing we are using a designing or manufacturing the fiber. In that particular case, what happened, there are some impurities in a glass. So because of that particular impurities, absorption is takes place. So absorption of a signal takes place means what, there will be a signal attenuation because of those impurities present in a glass. Now what are those impurities present in a glass? I think we have discussed one particular table, and in that particular table we have mentioned that some of the common ion impurities in a glass, that with the absorption, one particular absorption peak wavelength. Now, just I'll draw again that particular table here. So that what about the impurities, or we can say that impurities, or we say that whatever the particular material available there. Okay, in that particular glass material. Now you can see that this is about a peak wavelength. The meaning of the peak wavelength, at this particular peak wavelength, there may be a large attenuation. That large attenuation is what? 1 part in 10 to the power 9 dB per kilometer. So now what are those impurities? That impurities in a glass, and that impurity are nothing but what? Cr3 plus. Okay, Cr is to 3 plus, and it has a peak wavelength of what? A 625 nanometer. That is about the peak wavelength. And attenuation is about a, what we can say, it is about a 1.6. Then a C2 plus, it has a 685. Then attenuation is about zero point 0.1. Then a Cu2 plus, then it has a peak wavelength of 850 nanometer, and attenuation is about a 1.1. Then Fe2 plus, it has a peak wavelength of 1100 nanometer, and that attenuation is about a 0.68. Fe raised to 3 plus, we have this that 400 nanometer is the peak wavelength, and that is about a 0.15. Then Ni 2 plus 650, what we can say, that is about wavelength, and it has a zero point 0.1 of a attenuation there. Means that zero point 0.1 of attenuation means what? That is a 1 part in a 10 raised to power 9 dB per kilometer. So I'll show you one particular graph. So in that, how much will be the attenuation for the intrinsic absorption and the extrinsic absorption taking place there, and what will be the total loss. So that total loss is depending upon that your fiber operating at what particular wavelength. So means all this attenuation occur at a particular wavelength. So that's why for a fiber optic communication, that wavelength is important. So at that particular wavelength means what, for this particular material I am saying, for example here, this material, or this we can say that the about a copper. So means at this particular copper, this particular material, what happened, at 850 nanometer of a wavelength, there will be attenuation of 1.1. If we are using the wavelength, that glass is made up of this impurities. Okay, that is about a glass is made up of this particular impurities, and in that case, and they have the, they are that glass means that particular fiber is it operating at 850 nanometer of wavelength. Then there will be a loss of what? 1.1, then one part in it 10 to the power 9 dB per kilometer. That is about a loss. Now, is for a given impurity is there, because we are designing a fiber core and a cladding. That core is made up of a silica glass and a mixture of some metal there. And in that case, while manufacturing the glass, these are some impurities used in a glass there. Now, these glass impurities, okay, they have the attenuation at this particular peak wavelength. Means we can reduce that particular attenuation for a given particular material, okay, for this particular material by using the different operating peak value. Which we can consider that supposed to be, we say that this particular material is there are the impurities, then this is to be operating at 850, then there will be attenuation. If we go for the other wavelength, so there won't be any. There may be attenuation, but that attenuation is low as compared to the what we are saying at 850 nanometer of a peak wavelength. Then we can reduce that particular impurities while manufacturing this glass there. Now, glass is to be manufactured whenever we can say that a glass is manufacturing with what? Because it is about just glass is to be heated first and then it is to be cooled one. Okay. While cooling, that vapor is to be removed. So if that means we can say that then the glass in the form of a liquid when it is heated, and when that glass when it will be a cooled. So that process of that heating and cooling takes place while manufacturing that particular glass there. And then that particular at the time of manufacturing, that process added some water molecules or some water dissolved in that particular glass there because of that heating and cooling. So because of that uh, water molecule, so means we can say that there may be a we can say that there may be a hydroxyl ion. Okay, we can say that a hydroxyl ion, or we can say that is about the OH ion. Now this particular hydroxyl ion or a OH ion, that will be added while manufacturing, and because of that, that loss, okay, because of this hydroxyl or a OH ion, that absorption will be takes place, or we can say that attenuation of a signal takes place, and that is called as a extrinsic loss. So that extrinsic loss can be minimized, or we can say that when we consider this particular graph to be operating at a different spectrum, okay, different wavelength band. So now one particular graph is there, it is showing that here is a absorption spectrum for the hydroxyl ion, okay, that is about the absorption spectrum for this hydroxyl ion group. And in which if you see that in this particular case, now you can see that this one we have the absorption of spectrum there takes place. Now this is about a operating wavelength, this one is about a operating wavelength. If we say that 600 nanometer, 800 nanometer, okay, likewise, that is about a operating wavelength 1600 nanometer. Generally, our fiber operating at 850 nanometer or 1350 nanometer or a 1550 nanometer, likewise. Now, at that particular uh, window or that particular band, if you see that there will be alternate. Okay, now you see here. Now, this is about a, if you take a here, so it is about that absorption. Because of that absorption, overtone will come because of this particular hydroxyl group in that particular silica. Okay, because of that, at this particular maybe approximately it is about a 750 or a 770 nanometer of a wavelength. At the 770 nanometer of a wavelength, there will be attenuation. Again, here if you consider here, it is about below 1000, maybe 950 or 970 something. There will be a attenuation. Now here you can see that a first overtone here, it is about showing that a 14, 15 something. Okay, likewise there will be a attenuation. So apart from that, there will be a attenuation again. Here we can say that there will be attenuation again at this particular band of a frequency. Now this attenuation occur here. This graph is showing that hydroxyl group, okay, because of that OH ion, because of that OH ion, that absorption takes place. Means attenuation takes place. That signal attenuation is takes place, and that signal attenuation at this different band. Okay, that this graph is showing that a signal attenuation at a various band. Now we can remove that. Okay, we can use a fiber for a given particular uh, wavelength, or we can develop a fiber that will not generate this particular hydroxyl ion, so that that loss can be minimized. So if you consider that, so there will be a loss. Now from this here, if you consider that that loss is less here, but loss is larger, loss is lower. Means similarly, if you consider that the fiber can be operating at this particular window here, that loss is minimized. Okay, now you can consider here this is about a graph and this is about a one here. In that case, there will be loss as compared to this value. So that loss will be there. Okay, so likewise, we can use a fiber here. Now you can see that this one above that 1500 something, that loss will be minimized there. So if you use a fiber with a 1500 nanometer of wavelength, in that case, that output reduces here. Okay, that attenuation will be reduces there. So now then we have seen one particular graph here earlier in a intrinsic absorption. So in that intrinsic absorption, that graph is showing that. Uh, Wait a minute. Let's show you that graph that is about a total loss and all. So that is about a one graph is showing that there will be attenuation, and that attenuation is about at this particular wavelength. Okay, that page I have missed here now. Even I can show you that particular here. Okay, that graph. So that is that will showing you that what will be the total attenuation. Okay, now this one. Now you can see here that is about a photon of energy. Okay, that part is about that total energy, because we can say that at a near infrared, what will happen to the fiber, okay, or below that infrared region. So what will happen? Now we consider that that is about the energy part. Now this one is about a motion here. We can say that is about the operating wavelength. Okay, this one is about the operating wavelength, and this one is about the attenuation. Now for this given particular wavelength, there will be a ultraviolet absorption. Okay, there will be ultraviolet absorption, and above this, there will be a infrared absorption. Means your we can say that that operating wavelength, if you consider that it is about the 1.5 micrometer, or 1550 1500 nanometer something. So above that 1500 nanometer, there will be a attenuation. That attenuation is about what you can say that attenuation due to that infrared absorption, and below that there will be a ultraviolet absorption. But again, if you consider that photon of energy, means we can say that a total power generated by this particular source, and it that particular signal have that much of a power that is to be propagating through the fiber. So when we increase the that photon energy, whichever the signal propagating through the fiber, if we increase the energy of that particular fiber, then what will happen? That signal get attenuated because of that increasing the power there. So for a given particular optical fiber, how much is the minimum optical power to be transmitted? Okay, that will be depending upon that what type of fiber we are using. In the case of a single mode fiber, so that they have the limitations for what? Operating power. Okay. If we use a multimode fiber, then in that case, that limitations somehow it can be reduced. But in the case of a single mode fiber, there may be a scattering losses. Okay, that losses will be more. Even that we can say that absorption is more there. Okay, means attenuation is more. But in the case of a multimode fiber, somehow we can minimize those scattering. Okay, we can minimize the loss there. Now this is about a realized scattering. In the realized scattering means what? For a given photon of energy, that scattering takes place. That scattering takes place at this particular wavelength. So this graph is showing this is about a dotted line, this is about a realized scattering here. This one is about a ultraviolet absorption. This one is about a infrared absorption. And this graph is showing about what? That is about the total loss. Now you can see that loss is minimum at this particular point, but gradually it will be increased because of infrared absorption above that particular band of a wavelength occurs. So means your fiber will operate at a specific band of a wavelength, and then attenuation will be reduced there. So similarly here we have the extrinsic absorption. We say this one is about a graph. It is showing that there may be a, we can say that a hydroxyl group in a silica, and because of that hydroxyl group in a silica, we can see that there may be a absorption takes place at this particular wavelength or at this particular band there. So now that attenuation will be minimum for a given particular wavelength. Now suppose to here, likewise. Okay, it can be minimized. Again, another graph is indicating that what will be the attenuation for the given wavelength. Now this was about the attenuation here. This one is about the wavelength we have. Now that attenuation, if we have the attenuation is less than this point something, we can say that 0.2 dB or 0.3 dB something. Okay, 0.02 dB something, and that is about it. That absorption is because of that, loss is because of that waveguide imperfection. Waveguide means what? Guide means what? It is a fiber because it guiding our signal. So that's why it is called as a waveguide. Now, then this absorption, we can say that ultraviolet absorption for this band of frequency. Your attenuation is reduced when we increase the wavelength. But if we increase the wavelength, then there will be infrared absorption. Okay, this is about a infrared absorption. And this one is about a realized scattering. Okay, this one is about a realized scattering. And this figure is about the attenuation spectrum for an ultra low loss single mode fiber. Okay, this is about a ultra low loss single mode fiber. As I told you earlier, that losses are there because of that single mode fiber. Why that losses are there in a single mode fiber? Because of that angle, we say a numerical aperture angle. And that numerical aperture angle will be small when we use the single mode fiber. If it is a multi mode fiber, that numerical aperture, or you can say that acceptance angle, that will be large. And then because of that, there may be a losses if we use a single mode fiber. But if it is a multi mode fiber, in that case, that core diameter is large, numerical aperture is large, so that's why that attenuation will be is small there. Then next is about a linear scattering. Okay, so we can consider that this one is about a extrinsic absorption. Next one is about a scattering. Okay, that is about a scattering loss, or you can say that is about a two type. That is about a linear scattering or a non-linear scattering. That is about a scattering loss means what? That whichever the signal transmitted through the optical fiber, and then due to the scattering means what? Because of some impurities there, that signal, okay, transfer all of that particular optical power within that particular mode, that will be transferred to the other mode. Means your signal is propagating, okay, it has some propagating mode, okay, whatever the it has a propagating mode, and that your signal is in one propagating mode, it will transfer to other mode. It will transfer the to the other mode, and that transfer takes place. That transfer will be takes place. That will be linearly. That's it is called as a linear scattering. So means your signal, you can say that a linear scattering means what? It is just a mechanism of transfer of some of the optical power. Okay, that is about this is about a propagating mode. It has some optical power. Some of the optical power that may be transferred linearly to the other mode, and that is called as a that we can say that that is called as a linear scattering. But due to the transfer of a power from one mode to the another mode, so that transition, okay, the transfer of this power from one mode to the another mode, and that transition will, we can say that that reduces the that signal level. Means that is nothing but a loss. That loss is nothing but we can say it is about a scattering loss. Means because of this transferring of the power, there may be a what? A attenuation we say. Means there will be a loss. Means signal get attenuated. So that's why you can say that is about the attenuation, because of that transmitting that a signal from one mode to the another mode. Means we can say that we have a fiber, okay, we have the fiber. Generally we are expecting that the signal is to be propagating, okay, signal will be propagating through the reflection now. But what happened here in the case of the fiber, so this particular wave or this particular ray has some particular frequency, okay, it has some particular lambda. But because of that scattering, that variation in the wavelength occur. Okay, variation in the wavelength occur means what? Variation in the mode occur because of that scattering. Means whatever the propagating mode, they have some supposed to be. I'm saying it has some wavelength lambda, but after that they have some variation in the wavelength there. Okay, means you can say that that is about a mode will be means mode is what? There is a difference in the frequency there. Okay, that mode is, we can say that is about a difference in the, sorry, now this mode means what? Propagating mode have some particular wavelength. Okay, propagating mode have some particular wavelength. When it transfer to the other mode, when it will transfer to the other mode, then what will happen? That there may be a variation in the frequency. Because of that variation in the frequency occur, signal propagating, or you can say that this particular fiber will work only for X mode, okay, that particular mode. When we transfer to the another mode, then what happen? Propagation of that particular fiber, that propagation of that particular ray, because of that variation in the difference in the mode will occur. Because of that difference in a mode occur, that propagating signal may not be radiating in this particular fiber, or may not be propagating within this particular fiber. Okay, so means they will not propagating, means after the changing of the mode, that signal will not propagating, or they will not continue to propagate in this given mode. Okay, and that they are not continue to propagate means what? They will radiate inside the fiber. Okay, inside. So that is because of that particular radiation. Because of that particular radiation, we can say that it get heated. Okay, fiber get heated. Okay, let that the part another part. Because of that radiation, there may be a loss of a signal occur, and that loss is nothing but the attenuation. We can say that attenuation is, okay. Because of that, generally we can say that there should not be a change of frequency while scattering. Okay, because we can say that because this is nothing but a linear process, and because of that linear process, there should not be changes in the frequency while scattering. But what happened there? That mode will not allow to propagating through the fiber, because that fiber is made up of that that will operate only that particular mode. Okay, so that's why there may be a radiation by that particular ray is propagating through the fiber. There are the types of a scattering. One is about, we can say, a realized scattering. One, and another is about a Maya scattering. Now, in the case of a realized scattering, what happened here? This scattering occurs. Okay, why this scattering takes place inside the fiber? Why these modes are changes? Okay, because we earlier we say that fiber has a intrinsic absorption and a extrinsic absorption. Now, in the case of a intrinsic absorption and extrinsic absorption, again we say that fiber have the absorption at the near to the infrared window. Okay, they have the absorption that will be near to the we can say that near to the infrared window. So if you see the graph, it is showing that graph is showing that they have the absorption near to the this one. This is the body graph. It is saying that there will be a absorption near to the infrared region. Means above this particular wavelength, okay, above this particular wavelength, there will be a infrared absorption. Now, in the case of a relay scattering, what happened at the time of manufacturing? Okay, at the time of manufacturing, so that density of that, uh, we can say that inside this particular fiber, that fiber core and all, that density will be changed. Density of that composition will be changes there. Okay, means in another way we can say that for a given particular fiber, because we can say that it is about a at the time of manufacturing. Sorry, at the time of manufacturing, there may be changes of the density of a composition there. Okay, there may be changes in the density of a composition, and due to that, so due to that, whichever the composition we are using, and the density will be vary. The density will be vary. How this density will be vary? Because when we manufacturing the fiber, we supposed to say that a core, okay, we supposed to say that a core of a fiber throughout this radius, okay, means you can say that this is about nothing but the radius of a fiber there. While manufacturing, okay, while manufacturing that particular fiber, in that case, that core refractive index will be vary. There may be a fluctuation in the refractive index. Generally, we say that a core and a cladding, they have the, okay, if we can use the tape index fiber, they have the constant refractive index. Okay, they have the constant refractive index. But in the process of a manufacturing, that refractive index of a core may be varying. Because of that variation in this particular refractive index, or we can say that there may be so variation means what? Just like I'm just saying now, from this now, we say at the center there will be a n1 here. Now if you go again here, there will be a small variation. But again here same value will be. Because of what we can say that this particular variation occur at the time of a manufacturing. And that at the time of manufacturing this n1 variation is occur. So we know that whatever the velocity of a propagation of this particular signal is depending upon that what will be the refractive index there. Okay, so this is approximately we say. Now, what it is saying? It is saying that velocity changes means your variation in the wavelength occurs. Okay, that particular part. So you can say that for a given uh, a signal propagating through the fiber, they have some particular wavelength now, and there may be a variation in the velocity. Okay, now this particular variation in the refractive index occurs because at the time of manufacturing, so we are expecting that that core is to be a same refractive index, but due to the manufacturing process, that variation in the refractive index occur inside the fiber. And why this variation occur? Because of that composition. Okay, that composition changes at that particular place because we are cooling that fiber is to be cooling. Okay, or we can say that initially it is in the form of a, we can say, a liquid then solid. Okay, likewise, and then we can cool it, and likewise that is about the manufacturing process. So if you consider that a glass, when we cool that particular glass, so that internal composition of this particular fiber changes. So because of that changes in the composition, that refractive index will be changed. And because of that refractive changes in the refractive index, so that rays propagating through the fiber, they will be scattered. And that's why we can say that is about a scattering loss. Now how to minimize this scattering loss? So at the time of manufacturing, we need to take care of there should not be any variation in the refractive index, okay, inside this particular core. So we can improve the fabrication technique so that when we cool the glass, the composition of that particular core should not be changes, or there should not be any refractive index variation because of that cooling that particular glass, or we can say that when we cool it, so the density will be changes, and that density is depending upon that material. So that's why we can say that there may be a relay scattering occur. Now that relay scattering we can write in terms of equation again. That is about a relay scattering coefficient gamma r here 8 pi cube by 3 lambda raised to 4. Okay, that is about, we can say it is about a refractive index n raised to 8, and that refractive index of the given medium for this particular core we consider raised 8 into p square. That is about the fiber, we can say that is about it has a photoelastic coefficient. That photoelastic coefficient at a given particular temperature. So that's why we need to consider the temperature also, and we need to consider that isothermal compressibility at a given particular temperature, that is to be considered this beta C factor. Then we can say that that is about a Boltzmann constant, and that is about a fictitious temperature of this material. Now this one is your refractive index. Then we can say that is about lambda is nothing but a optical wavelength. Your fiber will be operate at that particular optical wavelength. This P is nothing but what? Average photoelastic coefficient. Then we have this beta C is nothing but what? The isothermal compressibility at a fictive temperature. Then TF is nothing but what? Effective temperature. Then we have this K is equal to Boltzmann constant, and this will give us the what will be the uh, realized scattering coefficient of a optical fiber. Now, if you see that this realized scattering coefficient is depending upon that photoelastic coefficient, and again that effective temperature. Because that temperature is varies, okay, because that temperature is varies because at the time of manufacturing, that given particular fiber has a different temperature, and then we are cooling that particular fiber there. Means that at that particular state of equilibrium, what will be the temperature of that particular glass, and that glass that will be at that particular temperature, that glass will produce some particular loss there. Means that when we can say that signal is propagating through the fiber, there may be a loss, and that loss because of that particular fictive temperature of the fiber there. And then that means your rays are propagating through the fiber. Okay, so that rays are propagating through the fiber. So that loss is nothing but a transmission loss, because signal transmitting from this end to that end, because of that manufacturing defect inside the particular fiber. So that loss will be occur because signal gets scattered, and because of the scattering, radiation takes place, and due to the radiation, attenuation will be increases there. So that loss is called as a transmission loss of the fiber there. Okay, that is about a loss of the transmission loss of the fiber, and that transmission loss of a fiber is depending upon that what will be the length of the fiber. Based on this particular length of the fiber, we can consider that how much will be the loss occur inside the fiber. So relay scattering is again depending upon that what will be the length of the fiber. Again, it will be depending upon that operating wavelength. So if you consider the graph earlier, I have shown you. So relay scattering. Okay, now here. Now in this graph, now at a zero point 0.8 micrometer means what? 800 nanometer. Okay, at a 800 nanometer. So relay scattering is higher, means attenuation due to the relay scattering is higher. But if you proceed further at a wavelength of supposed to 1200, that relay scattering loss is reduced now. Means relay scattering loss is reduced if you increase the that wavelength. Okay, if you increase the wavelength there, by increasing the wavelength, relay scattering loss will be reduced there. Okay, are you getting? Means just simple. Relay scattering losses will be increasing by increasing the uh, wavelength there. Means for the long wavelength, okay, for the longest wavelength, that relay scattering will be reduced. Next, we consider that a Maya scattering. So we'll consider this factor because at a particular operating wavelength, the scattering will be increased or a decrease. Because when we see that your relay scattering is varying according to the this is about attenuation and this is about your at it will be reduced. The relay scattering will be reduced when we increase the wavelength there. We'll see that numerical regarding that relay scattering later. So now next about we consider that another scattering is about a Maya scattering. Now this Maya scattering is again it is about the that is a non-perfect, okay, non-perfect, what we can say, that is about a cylindrical structure. Okay, so now because of that non-perfect cylindrical structure, because we are expecting that for a given particular fiber, okay, like what it's supposed to be, I just draw here now. This is about it. a cylindrical structure. Okay, it is nothing but a cylindrical structure. So means in another way, I is supposed to be I draw here. This is about a core of a fiber, and this is nothing but a cladding of a fiber. Now this core and a cladding. Okay, this one is about, you can say it is about a core, and this one is about a cladding. Now in the case of a core and cladding, if we are using a step index fiber, that throughout the fiber they have the constant refractive index, and then there will be abrupt change in the cladding now. Okay, step index fiber, because at the time of manufacturing, that they are not able to maintain that particular cylindrical structure. For example, I am supposed to draw again here. We expected that it is to be straight now. So because of some variation occurs, so that will be a fiber. It is not a straight one. It will be a small variation at the boundaries. Okay, just I just draw here. Likewise, your fiber will have the boundaries. It is not a perfect cylinder one. Due to the imperfect cylinder or irregularities at a core and cladding interface, or there may be a difference in a core and cladding boundaries. Okay, at this particular boundary, or there may be a fluctuations in the diameter, because if you see that diameter is varying here, diameter is varying here because there is a fluctuations in this particular boundary, and that occur, or there may be a bubbles inside the particular fibers while manufacturing, because that bubbles is of oxygen vapors, or we can say the hydroxyl ion vapors, or air something, that is about it, bubbles or some strains are there inside the fiber, and because of that there may be a loss occur because of that non-perfect structure of the fiber. Now this one my scattering is about because of that non-perfect cylindrical structure. Because of that non-perfect cylindrical structure, the diameter of a core may be vary. Fluctuations in the core diameter, fluctuations in the core and cladding boundaries, fluctuations in the we can say that fluctuation in the refractive index inside the particular fiber, or there may be a bubble at this particular boundaries occur. Likewise, that particular bubbles are there that will be occur at the boundary there. And because of that, there may be a attenuation occur, or there may be a scattering of this particular light takes place. Scattering means what? When it your signal reaches at that particular boundaries or that particular bubble, okay, when your signal reaches at that particular boundaries, what will happen? It will be scattered at any other direction there. It will be scattered. That is called as scattering. Your signal will be scattered at that particular place. When it reaches at this particular place, it is propagating, but it will be scattering in the different various direction, and that is called as a scattering. Because of that, structure is not perfect one. Because of that imperfect structure, because of that imperfect structure in the fiber, and that will gives us that because of that imperfect structure there may be a loss, and that loss is depending upon what will be the type of a structure and what will be the variation in the particular fiber there. So we can reduce that loss. Okay, we can reduce that my scattering at we can reduce because of that proper or a perfect manufacturing of the fiber, or perfect manufacturing of the uh, that core and cladding boundary. How can we can reduce that? Removing that whatever the imperfections occurs at the time of manufacturing, we can improve the manufacturing process. We can improve that whatever the coating used in a core and a cladding boundary there.